Hello everyone, welcome to this lecture. In today's lecture, we are going to continue with the examples based on relations. Here the question is, let x equals to 1, 2, 3, 4, 5, 6, 7, 8 and r equals to xy, where x minus y is divisible by 4. Write members of R and show that R is an equivalence relation. Draw the graph of R and write the relation matrix. Here one set is given, which is x equals to 1, 2, 3, 4, 5, 6, 7, 8 and the relation is defined as write all the ordered pairs where the subtraction of both the elements is divisible by 4. Here I have written the Cartesian product x cross x, which is 1, 2, 3, 4, 5, 6, 7, 8 cross 1, 2, 3, 4, 5, 6, 7, 8. You already know that Cartesian product is where every element of first set is connected to every element of second set, which means one will be connected with all the elements of second set, which I have written here 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7 and 1, 8. Similarly, 2 is connected to all 8 of them. Similarly, 3 is connected to all 8 of them and so on. So I have written the Cartesian product here, out of which you need to define all the elements which satisfies this condition. So you can see that if I take 1, 1 and if I take subtraction of both of them, it will be 0 and 0 is divisible by 4. So in relation R, the first element would be 1, 1. The next element would be 1, 5, because if I take 1 minus 5, the answer is minus 4 and which is again divisible by 4. 1, 2, 1, 3 and 1, 4 does not satisfy this condition. So we want to write 1, 2, 1, 3 and 1, 4. Directly we will write 1, 5. Next element would be 2, 2, because 2 minus 2 is again 0 and it is divisible by 4. Next element would be 2, 6, because 2 minus 6 is again minus 4. And similarly, we can write the other elements and 4, 8. The next element will be 5, 5 and 5, 1, because 5 minus 5 is again 0 and 5 minus 1 is again 4 and 4 is divisible by 4. So I have written 5, 5 and 5, 1. Next two elements would be 6, 6 and 6, 2. Similarly, 7, 7 and 7, 3. 8, 8 and 8, 4. So you can see all the elements are such that subtraction of both the elements is divisible by 4. From this Cartesian product, we have written all such ordered pairs. So this is the relation R. Here it is asked that show R is an equivalence relation. What is an equivalence relation? If a relation is reflexive, symmetric, and transitive, then it is called a equivalence relation. Here you can see that all AA type of pairs are present in R for all A belongs to R, which means x equals to 1, 2, 3, 4, 5, 6, 7, 8 and all the pairs where 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7 and 8, 8. For all A belongs to R, AA also belongs to R and it is called a reflexive relation. So R is a reflexive relation. AB belongs to R, BA also belongs to R, then it is called a symmetric relation. Here you can see for 1, 5 belongs to R, 5, 1 also belongs to R, 2, 6 is there, 6, 2 is also there. For 3, 7, 7, 3 is also present and 4, 8 belongs to R. 8, 4 also belongs to R. So, for every AB belongs to R, BA is also there in the relation. That's why R is a symmetric relation. Next one, what is a transitive relation? If A is being mapped to B, B is being mapped to C and A is being mapped to C element is present in R, then it is called a transitive relation. Here 1 is being mapped to 5. 5 is being mapped to 1. and 1 is being mapped to 1. For all AB belongs to R, BC belongs to R, and AC also belongs to R. That's why R is transitive relation. This condition is satisfied for all the elements in R. Here for 2, 6 and 6, 2. 2, 2 is also present. Similarly for 3, 7. 3 is being mapped to 7. 7 is being mapped to again 3. And 3, 3 element is also present. Similarly 4 to 8, 8 to 4 and 4 to 4 is also present. Here, the transitivity is satisfied for all the elements in relation. That's why R is a transitive relation. And the definition of equivalence relation says that if a relation is reflexive, symmetric and transitive, then it is called a equivalence relation. Here, we have proved that R is a reflexive relation, R is a symmetric relation, and R is also a transitive relation. So, we can say that R is an equivalence relation. Now we are supposed to draw the diagram representing this relation R. Here you can see 1 is either connected to itself or it is connecting to 5. And similarly, 5 is connecting to itself and it is connecting to 1. So, to represent these elements, we will draw two circles like this, 1 and 5. Here, 1 is connecting to itself. So, it will have a self loop like 1, 1. And to represent 1, 5, we will draw a line starting from 1 and it will end at 5. And similarly, 5, 5 is again a self loop and 5, 1 will be represented like this. A line would be drawn starting from 5 and it will end at 1. Similarly, next two elements are 2, 2 and 2, 6. 6, 6 and 6, 2. To represent those elements, we'll draw two circles. Here we'll write 2. Here we'll write 6. 2, 2, 2, 6, 6, 6 and 6, 2. We have shown these four elements. Next set of pairs are 3, 3, 3, 7, 7, 7 and 7, 3. Again, we'll draw two circles 3 and 7, 3, 3, 7, 7, 3, 7 and 7, 3. Next elements are 4, 4, 4, 8, 8, 8 and 8, 4. Again, we will draw two circles here 4 and here 8. 4, 4, 8, 8, 4, 8 and 8. 4. So, this is the graph representation of relation R. Now, we are supposed to write the relation matrix for R. We already know in the relation matrix, if an element is present, we write 1 and if an element is absent, we write 0. Here, for all these elements, we write 1 and for the rest of the elements from Cartesian product, we write 0. So, 1, 1 is present and 1, 5 is present. So, we are gonna write 1 in place of 1, 1 and in place of 1, 5. All the other elements from the Cartesian product are not present in R. So, we will write 0 in place of all of them. In the second row, 2, 2 and 2, 6 is present. 2, 2 and 2, 6 is present. So, I've written 1 over 2, 2 and 2, 6. Rest elements are absent. So, we are gonna write 0 for all the other elements. In the next row, 3, 3 and 3, 7 are present. 3, 3 and 3, 7 are present. So, we are gonna write here 1 and 1 here. The rest are 0 and so on. So, this is the relation matrix MR. Next question is, let a set X equals to 1, 2, 3, 4 and relations on it as follows, where R1 equals to 1, 1, 1, 3, 2, 3, 2, 4, R2 equals to 1, 1, 2, 2, 2, 3, 3, 2, 3, 3, 3, 4, 4, 3 and 4, 4. On the base of these relations, you need to answer the following questions, which are: Question A, give domain and range of R. Question B, is the relation R1 is reflexive? Question C, is the relation R2 symmetric? Question D, write R3 equals to R1 intersection R2 and is R3 reflexive? You need to answer all four questions. Here I have written the set which is X equals to 1, 2, 3, 4 and R1 equals to 1, 1, 1, 3, 2, 3 and 2, 4. We already know that the first element of the relation represents domain of that relation, which means all the first elements represent domain of R1. So domain of R1 would be 1, 2. Similarly, range of R1 would be 1, 3, 4 because all the second elements of the ordered pairs represent range of that relation. Here the second elements are 1, 3 and 4. So they are the range of R1. Next question is the relation R1 irreflexive? What is an irreflexive relation? If for all A belongs to set X, AA must not belong to R1. Then it is called an irreflexive relation, which means any AA type of pair should not belong to the relation. Then it would have been called as irreflexive relation. But here you can see 1, 1 belongs to R1, and that's why R1 is not an irreflexive relation. Any AA type of pair should not be present in the relation, then it is called an irreflexive relation. And if all the AA type of pair are present in relation, then it is a reflexive relation. Here some AA type of pair are present, which means 1, 1 is present, 2, 2, 3, 3 and 4, 4 are not present. That's why R1 is actually a non-reflexive relation. Next question is R2 symmetric? Why? Here I have written relation R2. We know that if for all AB belongs to R2, BA is also present in that relation, then it is called a symmetric relation. For all AB belongs to R2, BA should be present in R2. Here for 2, 3, 3, 2 is present. And for 3, 4, 4, 3 is present. So relation R2 is a symmetric relation. For all AB belongs to R2, BA is also there in R2. That's why R2 is a symmetric relation. Next question is R3 equals to R1 intersect R2, which means a new relation which is R3 is defined where we need to take into consideration the elements which are common in both R1 and R2. What are the elements which are common in R1 and R2? Here 1, 1 is common in R1 and R2 and 2, 3 is common in R1 and R2. So the common elements are only 1, 1 and 2, 3. So R3 will be 1, 1 and 2, 3. Rest elements are not common in both the relations. So R3 will be 1, 1 and 2, 3. And the question is R3 a reflexive relation? No, R3 is not a reflexive relation because if all the AA type of pairs are present in a relation, then it is called a reflexive relation, which means all 1, 1, 2, 2, 3, 3 and 4, 4 all should be there in R3. Then it would have been called as a reflexive relation. Here only 1, 1 is there. That's why R3 is not a reflexive relation.